Okay. Thank you, Paolo, for the support. So, welcome to everyone present online. It's my pleasure to introduce Dr. Isidoro González-Adalid Pemartín. The name is longer than the talk. And the background of Isidoro is in physics, in statistical mechanics. He got his PhD at the Universidad Complutense de Madrid under the supervision of Professor Victor Martin Mayor. Isidoro has been with us since July 2024, and today is going to give us a talk about a sort of ancient method in statistical mechanics, the microcanonical method, that we are trying to, in some sense, reviewing, because it has a nice feature that uses very few random numbers, and Isidoro will explain why it's good to try to avoid use random numbers in Monte Carlo simulation. So, Isidoro, the floor is yours. Thank you.
Thank you for the presentation, Massimo. Thank you for the opportunity to talk in these seminars. I don't know how many there are in YouTube, so being part of this is, from my point of view, it's something really amazing. And the truth is, the title is really long to explain what Massimo said better than I can say, but the truth is I'm going to talk about what I do for all the thesis, which is the Edward Anderson model, spin glasses. Okay, in particular in a more technical part of this problem, which is associated with the Monte Carlo simulation, where we have to generate so many random numbers, which is not free. So then optimize the use of this random number is a really important part in order to obtain a more performance code. Okay. I know we are going to cover so many different topics. The first one is the model, of course, the Edward Anderson model. So this is in the first part, I'm going to introduce the physical part of the problem. And then we can move to Monte Carlo simulation and to the most detailed part, which is the random number generator. So this part will be only introduction to each of these topics, because you can spend something like a university course in each of them. We don't have enough time. And at the end, I want to give you the main ideas of each of these topics to talk about the microcanonical approach that we have developed as a review of the microcanonical approach proposed in the 80s to apply for this Edward Anderson model. And at the end, I give you a summary of all the talk in a single slide in order to make easier to extract the main ideas of the seminar. One important thing is that in the first part, I'm going to introduce concepts that I will use after. So if someone have any question, it's better if you ask at that moment instead of wait to the end. Okay, so ask at the moment, because you can lose in the rest of the presentation. Okay, so now we can start with the physical part. The Edward Anderson model, in particular the AC model, appears in the middle of the 70s in order to explain a strain behavior at low temperature in magnetic alloys. This behavior is connected with the existence of a phase transition or a critical phenomena, which sounds something really hard to understand, but the truth is that it's nothing different from froze water into an ice cube or melt the ice into water, which happen at some critical temperature, which is now for everybody 0 degrees. Okay. But in the case of magnetic alloy, what happens is at high temperature, which is in the right side, okay, you have a completely disordered distribution of your system without any information. Everything is random. But when you go to low temperature, you cross this critical point, and now some structure start to grow and appear in your system. So now you have some kind of order phase. And when you go from one to the other, you cross this phase transition or critical point. In order to obtain this behavior in a really simple model, Edward and Anderson come back to some idea of Ising and length about a magnetic system. So they propose to consider a lattice in the space of linear size L, and in each node of the lattice you put some spin. One spin that in this case have only two possible states, +1 or -1, or blue or red, if you prefer to talk in terms of color. Of course, this spin have some interaction, which is given by the coupling J's that in the same way have only two possible values in this model. You can generalize the model, but today I'm going to talk about spins +1 and -1 and couplings +1 or -1. They are random along the system. So each spin is connected with the nearest neighborhood according to this coupling, which will be positive or negative. And finally, you have the Hamiltonian, or the function will give the total energy of the system, which is the sum of all the interaction between the spins. From this energy, you can notice that if the coupling interaction is positive, which is a ferromagnetic interaction, the system have less energy if the color of the spins is the same. In the other hand, if the interaction is negative, you must put the spins in with different color to obtain a lower energy. The problem here is that, as any other system, we prefer to be in a lowest possible energy state. So this produces that due to some spin have different interaction with the neighbors, it will be frustrated because cannot choose one of the states. Imagine that some spins, neighbors say, you must be red, and the others say, no, you must be blue. At this point, the spin cannot choose a single of the state, and we refer to this idea that the spin is frustrated. You can extend this idea to the complete system, and at the end, the problem is that you can put the system in so many different configurations. You can paint from many different ways the spins. And the system wants to be in one of the local minima of the energy. But there are so many different local minima, and the system cannot choose a single one. So the complete system is frustrated by the existence of so many different possible solutions or local minima for your problem. These ingredients are enough to have the complexity that permit you to model the magnetic alloys. The problem, as any other complex system, is that there are only a few examples where you can do analytically the calculus.
The coupling is random.
The coupling is random.
So everything is random.
At the beginning, yes. At the beginning, you start with random spins. You put some couplings randomly, but the couplings remain equal for the all the simulation.
You draw the coupling at the beginning, and it stays the same.
Yes, this is the quench. We talk about the quench.
Okay.
But of course, they are random.
Mm-hmm.
So, as any other complex system, the solution came from, okay, let's try with numerical simulation that allow us to connect the experiment with the theory. The problem is that this system have a very, very slow dynamics. So your idea is to put the system in some of these local minima and move the system to other new local minima to explore all the possible state of your system. But when you try to do this, you need a lot of time because you have to overcome these really high energy barriers, and this is difficult. So difficult that say that people have created computers only for solve this problem, like Janus 1 and Janus 2 in the Janus collaboration. Moreover, to give you an idea of how long will be this kind of simulation for a three-dimensional system, not really large, only 32 spins in each of the direction, you need 10 to 18 spin flips. One spin flip is the step of your simulation. So look how many is a huge number of steps in your simulation to be able to start to study thermal equilibrium, measure the
So
energy.
you set a point and then you switch the color of the neighbor.
Repeat.
So what is the spin flip? You change the color of the.
Yeah.
Oh.
I'm going to cover this in more details in a few slides, but the idea is this. You take the configuration and try to change the color of one spin. Sì.
Come no?
Okay, so at this point, you know the model, but it's true that knowing the model is not enough to start to think how we work this in numerical simulation. So the idea is, okay, I want to estimate the energy of the system, for example, at some temperature. When you go to the laboratory in experiment, you prepare some sampling, which are copies of the system, each of them in a different configuration, and then you measure the energy and say, okay, the energy at this temperature is given by the usual mean of my measure. The truth is that here you are approximated this integral, which is, okay, I have a probability distribution to obtain the system in this configuration, and the energy, the expected value of the energy is given according to this probability distribution. So the idea of the simulation is, I know from theory that in thermal equilibrium, this distribution is given by the Boltzmann distribution function, which has this expression, but the important thing is that you have this exponential with the energy. So when the system has a smallest energy, the probability is larger. The same I said before, I prefer to be in a local minima of the energy than in a local maximum, okay? So the idea of Monte Carlo simulation is, okay, I'm going to generate the same sampling as in the experiment, but in my case, I'm going to start from some configuration. I'm going to produce a new one configuration that follows this probability distribution. If I can do this, the work is done. Now you can start to do the same kind of measure that people do in the experiment. So the problem here is, how can I create this sequence of configuration of the system? And then we can move to the technical part, which is the Monte Carlo method. Monte Carlo method appeared in the middle of the 40s inside the Manhattan Project with von Neumann, Ulam, and Metropolis, where when they want to do some calculus about nuclear reaction, and they decide to move to a probabilistic point of view, and then appear the Monte Carlo methods. After that, people apply Monte Carlo method for so many different problems. Is one of the most successful numerical technique because you can apply, if I'm not wrong, to any kind of problem. I look to Maximo.
No, including solution of partial differential equation. Just to give you an idea.
Okay. But the truth is, you ask what is a Monte Carlo method, sometimes the definition of the answer will be a little bit difficult to understand. From my point of view, here I'm going to give you a more qualitative idea, but I expect that you obtain the taste of what is a Monte Carlo simulation. And it's nothing different than a numerical method to solve a really complex problem by random sampling. And to understand better the idea, I have a really easy example, which is imagine someone asks you to calculate or estimate the value of pi using Monte Carlo simulation. You know that a circle with a radius 1 have an area which is pi. And you can put this circle inside a square of side 2, of course. In this case, have area 4. So if you are able to estimate the value of the area of the circle by some Monte Carlo method, you can obtain pi. So you start to do your random sampling, which is nothing different than generate points inside your square. Some of them will be inside the circle, other will be outside. You repeat this process for a large number n, okay? And then you assume that, of course, the ratio between the areas of the circle and the square must be proportional or approximately equal to the ratio between the number of points inside the circle over the total number you generate. Putting together these two equations, you have a way to estimate the value of pi by only throwing or generating random points in a square. And this is all. More points, better approximation, of course. You can generalize this idea to measure, for example, volumes in a hyperdimensional space, which are this kind of integrals, so always the same. You generate points, and you approximate the volume by or proportional to the number of points inside your domain over the total number of points you need to generate. Not only for measure volumes, you can do the same kind of trick to do some integrals or any integrals in a numerical way. But always the idea is the same. You have some problem, which will be really complex. So you generate randomly some samples in the domain of your problem, and you use these samples to give approximate solution. At this point, probably you cannot be able to connect or do these kind of things to generate your sequence of configuration in the Edward Anderson model. But as I'm going to show you here, you only need 3 steps, okay? So we come back to the previous one model. Your lattice with the spins that are chosen randomly at the beginning, your coupling, which are chosen randomly at the beginning and remains equal for the rest of your simulation, and you start your process to generate a new configuration. The first step is, okay, choose one spin. And now you change the color. You try a spin flip. And here came all the trick, which is, okay, I'm going to accept this change of the color according to this probability, which is nothing different than if you reduce the energy, you always accept the change. Because I say you that the system prefers to be in a lower energy state. So always you accept the change. If you increase the energy, you accept according to this exponential probability, which, if you remember a little bit, the expression of the Boltzmann distribution is proportional. It's exactly the same exponential you have in the numerator. And this allows you to generate configuration that follow this probability distribution. Okay, so let's take a look to the example of this spin. Imagine that all the interactions are ferromagnetic, equal 1. So I came from a red one, I put in blue, I reduce the energy, so you accept the change. Now you take this other spin. Imagine all the interactions are ferromagnetic, so this spin is really happy because all their friends have the same color. you change. Now you increase the energy. So you need to accept this change according to this exponential probability. So you need to generate a random number, and if the random number is smaller than this probability, you accept. If not, the spin remains in the same color. You come back. And this is all. By repeating this process more and more times, you go from one random configuration to a new configuration that slowly go to a thermal equilibrium and follow the Boltzmann distribution. And at that point, you can start to measure and do whatever you want with your configuration. So the engine that move your Monte Carlo simulation is nothing different than random number generator. This part will be a little bit more technical, but I prefer to be not as technical. So for the people that want a more formal answer to what is a random number generator, please ask to Google or something like that, because here I'm going to give you 3 different definitions, which are qualitative but useful for understand what is a random number generator. The first one is something that allows you to sampling some probability distribution. This is a beautiful way to say a coin, a dice, a box with numerated balls. All of this allows you to sample from some probability. In the case of the coin, is the half probability to obtain one side, half to the other. Okay. The second definition is a source of entropy or noise. If you imagine the noise of a zone with noise, this is something with high entropy that seems to be random. Okay, in particular, it's random. It is white noise and this kind of things. Following this idea, people have developed or classified the random number generators as true random number generators because they use some process in the computer or directly some physical device that have access to some noise or entropy. For example, the noise inside your computer to generate a sequence of random numbers. Okay, this is not the most extended version. The truth is, this answer to the question gives you, which is the most extended version of a random number generator, which is something that generates a sequence without any pattern. Of course, you throw the coin, and sometimes you obtain a sequence, and there isn't any pattern that you can extract for the throwing coin. And following this idea, we have the pseudo random number generator. The idea of pseudo random number generator came from the fact that you generate a sequence, but a deterministic one, as I will show you. These generators, which are the ones I'm going to talk in the rest of the presentation, okay, in the rest of the talk, are characterized by a space of state, which is, for example, in your die is the number from 1 to 6. Here, of course, you have the number from 1 to, I don't know, 1 million or 1,000 million, okay? And a function that you can apply to every state of this space to obtain a new one. Of course, to start your sequence, you need the first one element of your sequence, and then you start to apply this function. As you know, if I give you the same seed, the same initial state, you obtain exactly the same sequence. This is a deterministic process, okay? And this is the difference and why this is called pseudo random number generator. One important thing is that if at some point you obtain a previous number, you start a loop. For example, if you obtain, after applying the function many times, the seed, you start again. So the pseudo random number have some period. It's periodic, and you want that the period is as much larger as possible. In principle, equal to the number of states you have. Okay, but
You don't want cycles.
you don't want cycles, so you want that the period is equal after cover all the possible states. This approach is using so many different subjects, of course, in science, but one of the most, say, important that use random number generator will be cryptography and cybersecurity to generate the keys to encrypt an email or something like that, or the two-factor authenticator that you use to enter in your email account, okay, or your bank account. So, of course, better random number generators, faster random generators allows you to have a more secure environment.
But it cannot be just a deterministic function, a random number generator. You must require something more than.
Of course. Give me one slide more. So many applications, there are so many different random number generators. Of course, this doesn't include all, there are more. Some of these are, the truth is, they are not a single one random number generator. It's a family of different random generators based on the same function, in the same state. People have developed so many different for many different applications, okay? What we need to have a good random number generator is that the function and principle the function I use make that the random number generator satisfy this list of properties. Of course, I want that the number generated must be uniform. We always try to generate in the uniform distribution. If not, I have a bias that affects my results. I want something independent from one state to the next one. I don't want some correlation. It must be independent. A long period, which you said before, unpredictable, which refers that if I give you some part of the series of the random number, you cannot predict the following ones. So it's impossible to extract the function. Performance, of course, you need 1 year to generate your random number. Your email will be there in 1 year, so, okay. And equidistribution, which refers to something like what we do in the calculus of pi, that if you generate the numbers points in a hyperdimensional space, there are not some clusters, so they must be uniform. Of course, test this for the random number generator is not easy.
I don't understand this independence. What is independence? Because
imagine that you generate a random number, and the following one are correlated.
This is unpredictable, no?
They are connected, but it's not the same.
Because the independence has to be something.
Yeah, but for example, imagine that the correlation is that when you go for some distance, you always obtain a random number, which is twice the one. So the correlation allows you to have some prediction, but will be different.
I don't see the difference. The difference between a distribution and uniform distribution.
Because the uniform distribution is you are generating numbers over the natural numbers, and you want something uniform, but
not in higher dimension.
Not in higher dimension. When you go to higher dimension, I use the same sequence. Will be that when you put the numbers to generate a point in this hyperdimensional space, they appear in some clusters. So, of course, it's difficult to check this kind of properties. And this is why people have developed so many different tests to check these properties of the random number generator. about the Monte Carlo value of pi is something that you can do now. If I give you a random number generator, you can do this kind of test. And also people group this test in a suite that at the end gives you the answer if this is a good random number generator or have some problem. Okay, but it's really difficult to detect this kind of thing.
There's a question by Flavio. He asks if change can happen simultaneously.
Change.
That's the way, Flavio.
If you want more information, probably it's preferable if you take a look to this book, The Art of Computer Programming by Donald Kuhn, but will give you more information, more detailed than the ones I can give you in
Isidoro, a small typo. It's the NIST suite, it's not the INST.
Ah, sorry.
Because if they try to find the INST,
sorry.
it's the National Institute of Standards.
Yes. Have more sense in this way. So after this review of these three topics, now it's time to talk about the microcanonical approach, which is nothing new. Okay, this is true, but in the way we apply to Edward Anderson model, it is. But before going details about the microcanonical approach, I will give you a taste of why we want to do these kind of things. I told you that to perform your Monte Carlo, you need to create a random number for update h-spin. If you need something which is reasonable, 1 nanosecond per generate a random number in your computer, the Janus simulation will need 30 years. Only for one sample. Of course, you want to study more than one sample. You want to study to repeat this process for many different samples of the number of 1,000. This is impossible. Nobody will give you a computer for 30 years to run your simulation. It's true that people have developed many different ways to solve this problem. One, for example, came from Gillespie, which is very useful when the probability to accept a spin flip is really small, which happens at really low temperature. The idea of Gillespie is that in the naive way, for each spin, you throw your random number and you answer the question. A change in color, a spin flip, which increase the energy is allowed? No, 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 no. And at some point, because this probability is really small, you obtain a yes. So after n question to this random number generator, you obtain an answer which is yes. For this spin, you can increase the energy. So the idea of Gillespie is, okay, instead of generate a random number for each of this spin, I'm going to randomly generate the number n. To do this, you work instead of directly with the probability p with a cumulative probability distribution f of n, and making the calculus, you can express this n as this function of a single random number, which you generate between 0 and 1. So with a single random number r, you expect to answer this for so many different spins. But what happens when the temperature is not so low? So the probability is not close to 0. In this case, you need other way to deal with this, but with the same idea of parallelize the random number generator. So in this case, imagine you have only 8 spins, and you do the same trick as in the naive way. In this case, you have more green dots representing the spins you can increase the energy. You can think in this as the binary representation of some number m. In this case is 90. Okay, so the green dots are ones, the red are zeros, and you perform the same idea. I'm going to generate a number m randomly where the numbers 1 have the probability according to this exponential. Okay? I give you the expression of the cumulative function in this case and the way you obtain the number n, but the idea is that you can generate a number where the probability of obtaining a 1 in the binary representation is given by the Boltzmann distribution. Of course, this is allow you to have a more performance simulation, but the truth is that you need around the half of the time of your simulation to generate a random number, the random numbers, okay?
So the model is you generate the number whenever you guess to meet the number.
Yeah. Sometimes you will need because you decrease the energy, but at the end you prefer to generate the guess that I'm going to allow or not the energy than wait, because in this case, if you wait to say, okay, I increase the energy, I generate a random number, of course you need to use the naive approach, and you cannot parallelize anything. In this way, you are parallelized over a vast number of spins. So you split the problem in what is the kind of spin flip I'm going to do, and if I'm going to allow or not the change. The next solution is, okay, I don't want to use random numbers. If I need to spend the half of the time generating random numbers, okay, don't use random numbers and everything is solved. The performance is multiplied by 2, okay? Cruz arrived to this idea in the 80s, inspired by the microcanonical approach used for studying many different systems, like molecular dynamics, where you put the system at the initial condition and it evolves following some, for example, the Newton law of movement, some differential equation. Nothing about random numbers. So he proposed this idea, okay, I'm going to use this kind of idea, a microcanonical approach, which have constant energy for a statistical model. In his case, he chose the easy model, which is exactly the same as the Edward Anderson, but now the couplings are all equal to 1. So all the couplings are permanent. And he needs to include an extra entity, which is the diamond. So now the total energy of the system is the energy of the diamond plus the energy of the spin.
So if the coupling is constantly equal to 1, you look for different color of the edges to minimize the energy.
You look for
different spins.
Different spins.
Opposite spins.
You always want to change the spins. The couplings, the edge are always fixed. You don't change the edge. The J's are always constant.
Yes, but you look for a configuration in which the edges are have two colors at the end. This is the ideal configuration, the minimum energy configuration.
For this lattice, you change the color in the nodes, the spins, for a colored lattice of edges. This is true. Now all the edges are equal 1, so they are black. Doesn't have any role in the calculus.
But the energy, how is defined in the field? Is the product, the sum of the product of the spins?
Yeah, because you can take the J outside the sum because it's constant, equal for all the.
And so, don't you look for a decoloring of the lattice in the room to minimize energy?
Yeah.
That's what I mean.
You always look to minimize the energy by changing the color of the nodes. If you
okay.
Okay, this diamond, of course, can move for the system, along the system, okay, has some energy, and it can take and give energy to the spin, so interact with the spins. So now the previous rule of accept a spin flip according to some probability is changed for a rule for how interact the spins with the diamond. If you decrease the energy of the system, the diamond takes this energy with him. In the case you need energy to change the color of the spin, the diamond gives the energy. So the diamond must have enough energy to give to the system.
But there is still a random movement of the demon. So
The demon can be moved randomly or sequentially. This doesn't change the dynamics. Here I show you a random movement that needs random numbers, but of course you can do this in a sequence way. That travel along
from row to row.
For example, go in X, all the X, change to Y, and after to the following plane in Z. Okay, the problem is that if you try to apply this to an Edward Anderson model, the code is not really efficient because you don't need random numbers, but the dynamics is slower, so you need to simulate for a long time your system. And this is why we propose a new implementation of the Cruz algorithm that in this case is hardly parallelizable, so we can use parallel computer like GPUs to have a more performance simulation. Your idea starts by, instead of have a single one diamond, we put n diamonds for each spin. In particular, we choose n equals 6 because I'm going to show you simulation in a three-dimensional system. So each spin have 6 nearest neighbors. So have 6 diamonds is something which looks more reasonable, okay, in some sense. Now the diamond have a maximum energy, so you can now give him whatever you want. There is a limit of the energy. And to deal with this problem, we need to refresh the energy periodically. So we decide to do this refresh of the energy of the diamonds at 2 power of 2 Monte Carlo steps. And the energy of the diamonds after the refresh is given by the Boltzmann distribution. At this point, you can ask, okay, but you are generating random numbers to generate the energy. But using this way of refresh only 8 power of 2 Monte Carlo steps allows you that the cost of generate this random number is diluted in the total cost of your simulation. So at the end is neglected. And in addition, you can perform this refresh in the CPU, for example, and run the rest of the simulation in the GPU. So in parallel. So at the end, generate the random number in this sense is free.
So K is fixed.
K, no, so you are refresh the diamonds 8 power of 2 Monte Carlo steps. So at 1, 2, 4, 8, 16, 52 Monte Carlo steps. Okay. So K, this is not a delay in some sense. It's not a space in time, always fixed. Increase in following this power law. Okay. Again, the diamonds are not fixed in some spin. They can move in a fixed direction. And now we have a new rule for the interaction between the diamonds and the spins. The first one is I want to increase the spin's energy the diamond must have enough energy to give to the system. But if you want to take energy from the system, the diamond must have enough space to take the energy. For example, in the case I show you here, if you want to give to the diamond 2 units of energy, you cannot do it because you have 3 maximum units of energy and you have 2. So this change is not accepted.
No, because you are like considering only one demon that is composed by the whole energy that is.
No, this is more in the line that if you want to simulate an infinitive energy diamond, you need at the end a floating point number to represent the energy of the diamond. However, if you put a maximum of 3 energy units, you can represent this with 2 bits. Sorry. So it's.
But each daemon moves freely in the network.
No.
Not exactly.
No. You have 6 demons, okay?
And each demons stay in a different spin, or they all stay.
No, you have 6 demons in each spin, okay? The first one move always in the x direction +1, okay? In the positive x direction. The second one move in the positive y direction.
So just at the beginning, they stay in the same spin. Then they move
They move.
freely in each.
Freely, but
Each
always
direction.
in the same
On the
direction.
lake.
Yeah.
You can do it randomly, but of course this have some cost because you need to generate random numbers. You need to change to choose between what demons you must change, so have a computational cost. And at the end, doesn't have any role.
I imagine that when a demon hits the boundary, he changes direction. He changes.
No.
No.
It's periodic
okay.
boundary condition. Sorry, it's periodic boundary condition. So come back to the beginning.
You are on the terms.
Yeah, they are in the third.
It's a three-dimensional.
So another question by Flavio. He asked whether this demon approach is realistic.
I will show you.
In a moment.
I will show you. Okay. So of course, when we know that the
It's not mine the question.
No. But I need someone to look to answer the question.
Choose one.
Okay. Of course, the first thing you want to do is to check if this kind of dynamics is real or not. So the best dynamics that mimic the nature we have is Metropolis. Okay, the usual Monte Carlo simulation that you produce known as canonical method, and we take data from the Janus collaboration. In particular, we study a 3-dimensional system in a large lattice, okay? And we choose to compare 3 different regions. The first one, which is the paramagnetic phase, where the spins are randomly, so reach thermal equilibrium is easy. The second one, which is close to the critical point, where we change from one phase to the other and everything starts to be harder. And inside the spingless phase, which is the phase with some order, where you cannot reach thermal equilibrium. And then we start to comparing our result with the Janus one. Here I'm going to show you the energy, okay? And in red, you can see the data from Janus in the usual Metropolis simulation, and in blue, the one generated with these dynamics of the microcanonical diamonds. Okay, you can see that in log-log scale, both dynamics are parallel. This is in the paramagnetic phase, so you can say, okay, but in paramagnetic phase, everything is really easy, will be associated with this path. So what happens when you move to a more difficult situation? This is in the critical point, and the data remains to be parallel. So this seems that you are in front of the same dynamics. And inside the spin glass, you have exactly the same. However, look at the plot and say that this is the same dynamics is not something really quantitative. So we try to apply a rescale of the simulation time in the microcanonical data by multiply the time by 6, which is the number of diamonds, and you obtain this beautiful plot where the blue dots are over the red ones. Or you can go more inside and measure the difference between both data. At long times, the data, of course, is compatible in the error, but which is more interested or fun to see is that at a short time at the beginning, you can notice that the effect of refresh the diamond. You can see that at some point, the energy of the system, the spins start to grow, which is the fact that you put all the energy in the diamonds. They cannot take more energy from the system, so you can only transfer energy from the diamonds to the system, so the system energy starts to grow. You perform the refresh, so you restart the diamonds, and your energy goes down really fast. After some time, this process is not noticed, so and you recover the usual dynamics. As a final idea, we test with some quantities which are time independent and don't have this effect of the refresh process, which are the correlation length of the system that give you information how far the information travel inside these clusters. And as you can see here, by doing nothing, you obtain one data over the other. So this is a confirmation that this microcanonical approximation, this microcanonical method, gives you the same dynamics than the canonical one. So this is a real dynamic that you can use to study the dynamic of this kind of system. And then I will finish with a single slide which summarize all the information I give you in this talk, which is that Edward Anderson model is a really complex model, so you need to use numerical techniques to study this kind of system. In particular, Monte Carlo simulation is the most extended one from this point of view, which have one of the problems to generate random numbers. One of the solutions is forget about random numbers, which was proposed by Hughes, with the problem that in the case of Edward Anderson model is not really powerful. In other cases, it is, but in this case, not. And then we decided to use this rethink. We reinvented the algorithm in some sense that can use the GPUs and parallelizable computing to obtain exactly the same dynamics that in the Metropolis algorithm. And this is all.
Let me add before I quit that the final goal is to design a new chip that can simulate the spin system with no need of random number, because to design the random number generator would be too complex, whereas to generate the chip just for the spin update is much simpler. So this is a sort of warm-up exercise to be sure that we can design a new chip.
Good luck.
Now the ball is in the side of the industry.
Oh.
I have a question. Why you call your methodology microcanonical?
It is for historical reason. The microcanonical ensemble in statistical physics suppose that the energy is constant. You work at constant energy.
In this case, you have the demon that carry on energy that can vary.
But the sum, I think, is
the idea is that the total system, the spins plus the diamonds, have the same constant energy in the Kreutz algorithm. And in our algorithm, not, because we are refreshing the energy of the demon.
So it is not exactly the microcanonical.
No.
Because you
The truth
start with
is
the
that you
energy.
live between both methods.
No, it's not a microcanonical. If you are refreshing the
No,
energy, no.
the truth is not, but when you are, for example, a really long time, you stop to refresh the demon because the next refresh happens in the after twice your time. So
You are
during a long time, you are in a microcanonical regime.
Okay. You are in the limit.
Yeah.
Okay.
Can you imagine some observables that carry on the memory of the fact that you have not generating a random number, but just following? I see that with the energy, the dynamics is practically the same. Also with the correlation, you can have a good agreement between the simulation with the demon and the simulation with the...
It's really difficult.
It's really difficult. Or
It's really
unlikely?
difficult. It's really difficult to notice this problem from the simulation. For example, I didn't work in this, but in the Janus collaboration, as I know, for L equal 24, they have some problem associated with the random number generator.
So
you introduce a bias in the model that can affect your simulation. Of course, if you have enough samples, enough replicas, and you can deal with it.
Because as I can imagine, the dynamics with the demon is, it seems quite regular because he moves straight on in his direction and then he can change it, which is very different from pick it at a random spin.
The truth is that you don't pick the spin randomly. You can do it. The truth is that normally what we do these kind of things in the metropolis way, so without diamond, generating a random number, you update sequentially.
Yeah, sure. You have a path. You have a Markov chain.
Yeah. So you start with the first spin, you go to the next one, you go to following this sequential way to update the spin.
Markov chain is stochastic.
Yeah. It's a Markovian chain. Yeah.
When you use the Monte Carlo method to obtain the Boltzmann distribution, you have a realization of a Markov chain.
Absolutely.
And I don't give you this idea, but you need that the dynamics, the rule, satisfy, which is called balance or the Tiley balance, which seems that the probability to go to one new configuration is the same that going from this configuration to the previous one.
Yeah,
it's not as simple as
So the demon chain is like a Markov chain.
The demon, only the demon, according to the energy, yes.
Yeah.
In particular, for example, in the work of Cruz, he showed you how you can extract, for example, the temperature of the system from the energy of the diamond.
But is that a mathematical reason for this?
There is a strong proof that justifies.
I'm not a mathematician, so. But as I understand, the idea that using in this way a Markov chain that satisfies balance is enough to be sure that at the end you are taking samples which follow the Boltzmann distribution. I think that the trick is that the Boltzmann, under this assumption, the Boltzmann distribution is an eigenvector of the Markov chain matrix. I don't remember the name. Sorry.
I can't believe. No. I trust you, but my question is there a mathematical explanation for the similarity between the section similarity of the two approaches, the Markov chain approach and the demon approach?
There are a work that shows you that in the thermodynamical limits, so in a huge system, both dynamics are the same. I don't know if it came from a mathematician or from a physicist. So, but for example, you can think that when you perform a metropolis or a Monte Carlo simulation, you can imagine that you put your system in contact with a huge energy reservoir, a system that can give you and take energy, whatever you want from the spins. And now imagine that in the case of the diamonds, you have millions of diamonds, much more than spins. So the diamonds act as this reservoir of energy that can take or give energy whatever you want.
Since they are as random.
Yeah.
In a sense, when they are so
and this is something that Kirut in his work discussed. There are some paragraphs saying, okay, if I refresh the energy of the demon each time I'm going to the next spin, I'm in a metropolis simulation, in a metropolis dynamic. If I have tons of demons, I'm in a metropolis dynamic because acts exactly equal that have a heat bath that take or give energy to the system.
So, more question?
Maybe the only drawback of your method is the memory consumption, maybe, because you have to have the 6 demon for each spin on your system. So you have to conserve the stock of energy for each demon.
You don't need to conserve the maximum energy. You impose the maximum energy.
The vector of energy, the value of energy for each demon. Okay, but
no,
maybe
also in the you can use a single demon, but of course you need to know the energy of the demon. Because if you need to take energy from the demon, you need to know
how many you have. If I am well understood, you have 6 demons for each spin. So if you have a 160 lattice with the 3 dimension, you have quite a lot. But with the supercomputer, no problem of memory.
Like you have an integer for each demon.
No, but at the end, the fact that we have a maximum energy for the demons, you can choose whatever threshold for the energy of the demon. But we choose 3 because the energy change in these spins happens as a maximum of 3 units of energy. Okay, when you make a spin flip, the energy can change in 4, 8, or 12. Okay, so you can quantify that 1 energy unit is 4, 2 energy unit is 8, and 3 energy unit is 12.
Okay.
So
thank you for your nice talk. See you, everybody.
So,
And stream.
no.
So.